All right, let's talk about one of the most mind-bending ideas in all of science, the many worlds interpretation. It's a theory that says every time you make a choice, a whole new parallel universe is created. So, is this actual science, or do we just wander into a sci-fi movie?
I mean, just let that quote sink in for a second. That's from physicist Bryce DeWitt, and he really captures the insane scale of what we're talking about. He was a key figure who helped bring this idea into the mainstream, the idea that our universe is constantly splintering into countless other realities. And this wasn't some fantasy novel, it was his serious attempt to solve a really deep puzzle about our cosmos.
So you gotta ask, why would anyone even come up with an idea that sounds so out there? Well, to get it, we first have to look at the incredible but deeply flawed theory that's supposed to explain our entire universe. You see, on one hand, we've got this theory called the Standard Model of Particle Physics, and it is, without a doubt, the most successful theory we've ever come up with. It's like the instruction manual for almost everything in reality, and it works with mind-boggling precision. But it's not the whole story. For all its success, this masterpiece has some major, glaring cracks. It has absolutely nothing to say about gravity. It can't tell us what holds galaxies together, dark matter, or what's pushing the universe apart, which we call dark energy. But the deepest, most fundamental problem of all, well, that comes from the very rules that make it work in the first place, the bizarre laws of quantum mechanics.
Okay, so let's zoom way in. Forget the cosmos for a second. Let's look at a single, tiny quantum event, because this is where reality stops making sense in the way we expect it to.
And right here, this is the heart of the mystery. The math of quantum mechanics tells us that a particle, before we look at it, exists as a superposition. It's basically a ghost, a cloud of all its possible locations all at once. But the instant we observe it, bam! That cloud of possibilities vanishes, and the particle just snaps to a single, definite spot.
To deal with this, the pioneers of physics came up with this idea called wave function collapse. Basically, they said, well, the act of looking at it just forces it to choose one outcome. But for a lot of physicists, that felt like a cheat, It describes what happens, but it doesn't explain why. It felt less like a deep law of nature and more like a rule they just tacked on.
And this is where the famous Schrödinger's cat paradox comes in, taking this idea to its logical, absurd conclusion. A cat in a box, its fate tied to a quantum event, is literally in a state of being both alive and dead at the same time. The math describes both possibilities perfectly. So what is it about us opening the box that forces reality to finally make up its mind?
Then, in 1957, a brilliant PhD student named Hugh Everett looked at this whole mess and asked a question that changed everything. What if the collapse never happens at all? What if reality never has to choose? Everett's proposal was both simple and totally radical. He said, let's just trust the math. If the equations say all these possibilities exist, then maybe they all exist. Every potential outcome of a quantum event doesn't just vanish, it branches off, creating a brand new parallel reality where that outcome happened.
This shows exactly how it would work. You start with the cat in that weird superposition state, both alive and dead. Then, the measurement happens. You open the box. But instead of reality collapsing, reality itself splits. In one brand new universe, a version of you finds a living cat. In another, totally separate universe, a different version of you finds a dead one. No possibility is lost, they just become separate realities.
Okay, but that brings up a pretty big question, right? If these other worlds are real, why can't we see them or feel them? The answer, according to the theory, is something called quantum decoherence. Think of it as the universe's way of building walls between these new branches, and it does it incredibly fast. It's what stops these worlds from interfering with each other and makes our own timeline feel solid and consistent. Now, as neat as all that sounds, you can't just go around claiming there are infinite universes without backing it up. For many worlds to be a credible scientific theory, it has to answer some really, really tough questions.
And there are two big ones. First, what's called the preferred basis problem. In simple terms, why does the universe split into nice, clean outcomes, like alive or dead, and not some weird, blurry mix of the two? And second, there's the probability problem. If every outcome happens somewhere, why does quantum mechanics give us specific odds for things? What do odds even mean if everything is a sure thing in some universe?
And once again, proponents say decoherence is the key. The constant interaction of a quantum system with its environment is what naturally weeds out those weird, blurry states. It forces the split to happen along clean, stable, classical-looking lines like alive or dead. The splitting isn't arbitrary, it's a natural result of physics that carves out these stable worlds we actually experience.
So, fast forward to today. After all these decades of debate, where does this wild idea actually stand within the physics community? Well, take a look at this. It's a poll of experts who work on the foundations of quantum mechanics. And while the old-school Copenhagen interpretation is still technically the frontrunner, look at many worlds. It is not a fringe idea. It is a major contender, taken very seriously by a significant chunk of the world's leading physicists.
Supporters, like the famous Oxford physicist David Deutsch, argue that many worlds is simply the most logical and straightforward explanation for what we see in experiments. He even suggests that when a single particle seems to interfere with itself, what it's really doing is interfering with its counterparts in nearby parallel universes.
But then you have the heavy-hitter critics, like Sir Roger Penrose. He thinks the whole theory is missing a huge piece of the puzzle: gravity. He believes that gravity itself is what stops big things, like cats or us, from being in two places at once. For Penrose, it's gravity, not observation, that forces reality to choose a single state.
And this really gets to the heart of the whole debate. The biggest issue for many worlds is that we can't test it. By their very nature, these other universes are cut off from us. So if you can't design an experiment to prove it wrong, is it really science? It remains this incredibly compelling, mathematically elegant, but ultimately unproven picture of reality.
Which leaves us with this incredible, almost dizzying final question. Is the single life you're experiencing just one story out of an infinite number? Is every path not taken, every choice you didn't make, playing out right now in another universe that's just as real as this one? The answer is still out there, somewhere in the cosmos.